We will continue our discussion of linear transformations in this video. So recall that a linear transformation is a mapping L that takes a vector space V into another vector space W. And the mapping has to satisfy two conditions for it to be linear. The first condition is that if you take a scalar alpha and multiply it by V and then apply the linear transformation, it's the same thing as applying the transformation to V and then multiplying by alpha. And if you have two vectors, I'm calling them V1 and V2, in your vector space V and apply the linear transformation, it's the same thing as applying the transformation to both of the vectors and then adding them in W. So this addition, if V and W are not the same space, the addition in V may be different than the addition in W, so you have to be careful there. So this is addition in V and this is addition in W, and also this is multiplication, scalar multiplication in V, this is scalar multiplication in W. Now if you want to check that something's linear, you have to first make sure that you're being sent to the right space, and you need to check these two conditions. You can check them individually, or you can combine them into one condition and just check this one condition. So you just need to check that alpha times V1 plus V2 and then applying the linear transformation is the same thing as applying the linear transformations to both of the vectors and multiplying the first vector with alpha. We also said in the last lecture that the zero vector is always sent to the zero vector in W. So the zero vector in V, apply the linear transformation, you're always going to go to the zero vector in W. We also mentioned that there could be other things being sent to that zero vector in W. But for sure, one thing that's always going to go to the zero vector in W is the zero vector in V. Now we're going to talk about what else could be sent to the zero vector in W. So the kernel of a linear transformation, L, that sends V into W, which we denote as ker of L, is defined by the set of all V in our vector space V, capital V, that's sent to the zero vector in W. So you're looking at all the vectors in capital V that when you apply the linear transformation, you get the zero vector in W. Now, it's obvious, let's put this in red, obvious that the zero vector in V is in the kernel, because we just said that the zero vector in V is always sent to the zero vector in W. So the kernel is never empty. There's always at least one element in the kernel, and the one element that we know for sure that's going to be in the kernel is the zero vector. Now that might be the only thing in the kernel, or there could be more things in the kernel. So the first thing we want to show is that this is actually a subspace of V. Why of V and not W? Because the kernel is all the vectors in V that when we apply it to L, when we apply L to it, we get the zero vector in W. So this is a set in capital V. So how do we show that this is a subspace? Well, recall the two things you need to show that something is a subspace. The first thing you need to do is for any V1, V2 in V, in the kernel of L, you want to show that V1 plus V2 is in the kernel of L. So we have to show that vector addition is in the kernel for the vectors in the kernel. And then we also have to show for alpha scalar and any vector, we can say V1 in the kernel. Scalar multiplication is also in the kernel. So write these down. I'm going to erase them so I have some space to actually show that this is a subspace. So you might want to pause the video and write them down. Okay, so let's show that this is a subspace of V. Okay, so we're going to let V1 and V2 be in the kernel. We want to see if V1 plus V2 is that in the kernel. Well, if we apply L to V1 plus V2, we want to see if we get the zero vector in W. So is that true? Okay. Well, what we do know is that since this is a linear transformation, we can break this into L of V1 plus L of V2. And I know that V1 and V2 are in the kernel, so L of V1 is the zero vector in W, L of V2 is the zero vector in W, and since this is a vector space, W, when we add the two vectors, the zero vector in W plus the zero vector in W, we get the zero vector in W. So you can see that L of V1 plus V2 is the zero vector in W. So V1 plus V2 satisfies this condition and it is in the kernel. So instead of a question mark now, this is a check mark. Let's check the other condition. Okay, so we're going to have some vector in the kernel, and we have a alpha scalar. What we want to see is if alpha times V1 is that in the kernel. All we have to do is see if we plug in alpha times V1, do we get the zero vector in W? Is that true? Well, what we do know is when we apply L to the vector alpha times V1, because this is a linear transformation, we can take the alpha out. And this is in the kernel, this V1, by assumption. So this is going to be 0, the zero vector, and any scalar times the zero vector is the zero vector. So we see that L of alpha times V1 is the zero vector. So we satisfy this condition. So alpha times V1 is in the kernel. Let's try a problem where we actually find the kernel. Suppose L is a linear transformation from R4 to R2, where any column vector in R4 goes to R2 by this mapping. So x1, x2, x3, x4 goes to x1 plus x2, so we add these two together, and x2 minus x3. We want to find the kernel. What I like to do is I like to rewrite the definition of the kernel. That way I'm thinking about it when I'm writing it, and I also get to see it, so it's easier to understand what I need to do. So what I'm looking for is all the vectors in R4, what we're starting with, such that when I apply my linear transformation to that vector, I get the zero vector in R2, which is 0, 0. How am I going to find this kernel? Now remember, the kernel is a subspace of R4. So let's see. Well, let's just start with the definition here. We're going to take any vector v, which is x1, x2, x3, x4, and this is being sent to x1 plus x2, x2 minus x3, but we want that to be equal to 0, 0. So what does that tell me? That tells me that x1 plus x2 is 0, and x2 minus x3 is 0. Okay, so let's write that down. x1 plus x2 has to be 0, and x2 minus x3 has to be 0. So x1 is negative x2, and x2 is x3. Okay, this is sort of like what we did at the beginning of the semester when we were solving a system of linear equations. What can we see here? First off, x4 is not even a part of this, so x4 is free. And we see that x1 depends on x2, and x3 depends on x2. So one of these is free. You can say it's x2. It really doesn't matter which one you call free. But if you let x1 be free, then that determines x2, and that determines x3. If you let x2 be free, you can figure out what x1 and x3 are. And if you let x3 be free, you can figure out what x2 and x1 are. So you can see that you have two free variables, x4 and x2. So let's write what the kernel is. The kernel is all, also I want to label that, since these are free variables, let's call this S for x2, and this is t. So remember that our vector looks like this, x1, x2, x3, x4. But now we can say, well, x4 is t, and x2 is s, and x2 is x3, so that's s, and x1 is negative x2, so that's negative s. So the kernel is the set of all vectors that look like this, such that s and t are real numbers. So we found the kernel, but can we find a basis for the kernel? Now this should remind you of the null space. It's very similar. Okay, how do we find a basis? Well, negative s, 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 t is equal to s times negative 1, 1, 1, 0 plus t times 0, 0, 0, 1. So then the kernel is the span of these two vectors. These vectors are linearly independent. You can see there's no way to get this vector from this one. And the kernel is the span of these two vectors, because you can see that any vector in the kernel can be written as a linear combination of these two vectors. So it's the span of negative 1, 1, 1, 0, 0, 0, 0, 1. Now, if I was to ask you what is a basis for the kernel, you're going to give me these two vectors. You're not going to say the span of these two vectors. That would be the entire kernel. When I ask you for a basis, I'm asking you for the vectors that would span the kernel. So just keep that in mind, that a basis, a lot of people on the test wrote span of the vectors. The basis is just the vectors negative 1, 1, 1, 0, 0, 0, 0, 1. And the kernel is the span of those vectors. Okay, I want to mention though, what would happen if you chose a different xi to be free? So what I mean is, what if instead, because I told you that obviously x4 was free here, but I said you could choose x1 or x3 to be free. So let's say I said x1 is free. How would that change what I've written over here as what the kernel is? Well, let's ignore that for a second. And let's say I said x1 is free. So then what we would have is s for x1, t for x4, x1 is negative x2, so then this would be a negative s. And since x2 and x3 are the same, this would be a negative s. And you could write this as s, 1, negative 1, negative 1, 0, plus t, 0, 0, 0, 1. And compare this to what we have for the kernel over here. What's the difference here? The only difference is this is a positive and these two are negative, and this is still a regular t. So when we pulled out the s and the t, you can see I have a negative 1, 1, 1, and here I have a 1, negative 1, negative 1. So the basis, you would say, is 1, negative 1, negative 1, 0, 0, 0, 0, 1. So when I did that, is the kernel the same? And the answer is yes, because this vector here, 1, negative 1, negative 1, 0, is a linear combination of this one. It's just negative 1 times this vector. So if you had instead put as a basis, instead of this vector here, you put 1, negative 1, negative 1, 0, you would get it correct, because this is a linear combination of that one. And this vector is linearly independent from that one, so it is a basis. All right, let's move on. Let me erase this. Okay, so let's let L be a linear transformation and S be some subspace of our vector space V. The image of that subspace S, which we denote as L of S, is defined as the set of all W's in capital W such that there is a vector V in S that's mapped to the W. So what you're doing is you're applying your linear transformation to all vectors in V. And what you're getting, which is called the image, the things that are in capital W, all the vectors that you find from applying L to your vectors in V, that is the image. So this is a subspace of V, and the vector space V is also a subspace of itself. So you could also talk about the image of the entire vector space. Now the image of the entire vector space, you can call it the image of V. So you could say image of V, just like I did here, the image of S, you could say the image of V. But you could also call it the range of your linear transformation. So what I erased earlier was L of V, which is the range or the image of V, is the set of all W in W such that L of V is equal to W for some V in capital V. So it's all the W's you get in capital W when you apply V. You might not get the whole vector space W. You might just get a subspace of capital W. So that brings me to an important point. The image of S and the range of your linear transformation, or you could say the image of your vector space V, are subspaces of W. Now why W? Remember that the image of these spaces is the set of all W's in capital W. So these are sets in W, not sets in V. The kernel was a set in V. The image is a set in W. And I claim that these are subspaces of W. Now this is a good exercise. Let's show L of S is a subspace of capital W. And as an exercise on your own, you can show that L of V is going to be the exact same proof that this is a subspace of W. So what do you have to show? That for all W1, W2 in L of S, and alpha scalar, alpha W1 belongs to L of S, and W1 plus W2 belongs to L of S. That's the definition of a subspace. That for any vectors in the subspace, if you add them, you're also in the subspace. Any scalar times a vector, that's also in the subspace. So if we say W1 and W2 belong to L of S, then there exists a V1 and a V2 in S such that L of V1 is W and L of V2, so W1, and L of V2 is W2. Why is that true? Well, if W1 belongs to L of S, let's look at L of S. If something belongs to L of S, then there's a vector V that's mapped to it. So since I'm assuming that W1 and W2 belong to L of S, you can find an element V1 that's mapped to W1 and an element V2 that's mapped to W2. Now what you're trying to show, so let's move over here. Let's put this in red. We want to show W1 plus W2 belongs to L of S. Well, you just need to show that there's some element that's mapped to W1 plus W2. Consider L of V1 plus V2. Well, V1 plus V2, we're assuming V1 is an S, and we're assuming V2 is an S. Since S is a subspace, this guy here belongs to S, so we can apply L to it. And because this is a linear transformation, this is W1 plus W2. So now you have a vector that's being mapped to W1 plus W2, so this is true. Okay, let's show scalar multiplication. So I'm going to erase this. You know, this would be a good exam question because it really tests your knowledge. I have to see if you understand what a subspace is, but I also am checking to see if you understand what the image of a linear transformation is. So things like this, there was a problem on the first test with the null space. This is very similar, so I think it's a good final exam question. Something similar. So the second one that we want to check is that a scalar times W1 belongs to L of S. So we're going to say W1 belongs to L of S, and alpha is a scalar. We want to show, so let's put this in red, show alpha times W1 belongs to L of S. Okay? So since W1 belongs to L of S, there exists a V1 in S such that L of V1 is equal to W1. Now, how do we show this? Well, let's think about it. We have to use properties of our subspace S. Now, S is a subspace, and we've defined a vector v1 in S. And since it's a vector space that is a subspace of the bigger vector space V, alpha of v1 belongs to S because it's a subspace. So let's apply L to that. Let's figure out what its image is in our vector space W. Well, this is a linear transformation. So this is alpha times W1. So now I have a vector in S being mapped to a vector in the image, and this vector is alpha times W1. So I have shown it is a subspace.